Section 8 of Climate Changes, Their Nature and Causes by Ellsworth Huntington. This recording is in the public domain. Recorded by Leon Harvey. Chapter 8. Some Problems of Glacial Periods. Having outlined in general terms the coming of the ice sheets and their disappearance, we are now ready to discuss certain problems of compelling climatic interest. The discussion will be grouped under 5 heads. 1. The localization of glaciation. 2. The sudden coming of glaciation. 3. Peculiar variations in the height of the snow line and of glaciation. 4. Lakes and other evidences of humidity in unglaciated regions during the glacial epochs. 5. Glaciation at sea level and at low latitudes in the Permian and Proterozoic eras. The discussion of perhaps the most difficult of all climatic problems of glaciation, that of the succession of cold glacial and mild interglacial epochs, has been postponed to the next in the final chapter of this book. It cannot be properly considered until we take up the history of solar disturbances. 1. The first problem, the localization of the ice sheets, arises from the fact that in both the Pleistocene and the Permian periods, glaciation was remarkably limited. In neither period were all parts of high latitudes glaciated, yet in both cases glaciation occurred in large regions in lower latitudes. Many explanations of this localization have been offered, but most are entirely inadequate. Even hypotheses with something of proven worth, such as those of variations of volcanic dust and in atmospheric carbon dioxide, fail to account for localization. The cyclonic form of the solar hypothesis, however, seems to afford a satisfactory explanation. The distribution of the ice in the last glacial period is well known, and is shown in Figure 6. 4/5 of the ice-covered area, which was 8 million square miles, more or less, was near the borders of the North Atlantic in eastern North America and northwestern Europe. The ice spread out from 2 great centers in North America, the Labradorian east of Hudson Bay and the Kiwatine west of the bay. There were also many glaciers in the western mountains, especially in Canada, while subordinate centers occurred in Newfoundland, the Adirondacks, and the White Mountains. The main ice sheet at its maximum extension reached as far south as latitude 39 degrees in Kansas and Kentucky and 37 degrees in Illinois. Huge boulders were transferred more than 1,000 miles from their source in Canada. The northward extension was somewhat less. Indeed, the northern margin of the continent was apparently relatively little glaciated, and much of Alaska unglaciated. Why should northern Kentucky be glaciated when northern Alaska was not? In Europe, the chief center from which the continental glacier moved was the Scandinavian highlands. It pushed across the depression now occupied by the Baltic to southern Russia and across the North Sea depression to England and Belgium. The Alps formed a center of considerable importance, and there were minor centers in Scotland, Ireland, the Pyrenees, Apennines, Caucasus, and Urals. In Asia, numerous ranges also contained large glaciers, but practically all the glaciation was of the alpine type, and very little of the vast northern lowland was covered with ice. In the southern hemisphere, glaciation at low latitudes was less striking than in the northern hemisphere. Most of the increase in the areas of ice was confined to mountains which today receive heavy precipitation and still contain small glaciers. Indeed, except for relatively slight glaciation in the Australian Alps and in Tasmania, most of the Pleistocene glaciation in the southern hemisphere was merely an extension of existing glaciers, such as those of South Chile, New Zealand, and the Andes. Nevertheless, fairly extensive glaciation existed much nearer the equator than is now the case. In considering the localization of Pleistocene glaciation, 3 main factors must be taken into account, namely temperature, topography, and precipitation. The absence of glaciation in large parts of the Arctic regions of North America and of Asia makes it certain that low temperature was not the controlling factor. Aside from Antarctica, the coldest place in the world is northeastern Siberia. There for 7 months the average temperature is below 0 degrees Celsius, while the mean for the whole year is below -10 degrees Celsius. If the temperature during a glacial period averaged 6 degrees Celsius, lower than now, as is commonly supposed, this part of Siberia would have had a temperature below freezing for at least 9 months out of the 12, even if there were no snowfield to keep the summers cold. Yet even under such conditions no glaciation occurred. Although in other places, such as parts of Canada and northwestern Europe, intense glaciation occurred where the mean temperature is much higher. The topography of the lands apparently had much more influence upon the localization of glaciation than did temperature. Its effect, however, was always to cause glaciation exactly where it would be expected, and not in unexpected places as actually occurred. For example, in North America, the western side of the Canadian Rockies suffered intense glaciation, for there precipitation was heavy because the westerly winds and the Pacific are forced to give up their moisture as they rise. In the same way, the western side of the Sierra Nevadas was much more heavily glaciated than the eastern side. In similar fashion, the windward slopes of the Alps, the Caucasus, the Himalayas, and many other mountain regions suffered extensive glaciation. Lower temperature does not seem to have been the cause of this glaciation, for in that case it is hard to see why both sides of the various ranges did not show an adequate percentage of increase in the size of their ice fields. For what has been said as to temperature and topography, it is evident that variations in precipitation have had much more to do with glaciation than have variations in temperature. In the Arctic lowlands and on the leeward side of the mountains, the slight development of a glaciation appears to have been due to scarcity of precipitation. On the windward side of the mountains, on the other hand, a notable increase in precipitation seems to have led to abundant glaciation. Such an increase in precipitation must be dependent on increased evaporation, and this could arise either from relatively high temperature or strong winds. Since the temperature in the glacial period was lower than now, we seem forced to attribute the increased precipitation to a strengthening of the winds. If westerly winds from the Pacific should increase in strength and waft more moisture to the western side of the Canadian Rockies, or if similar winds increased the snowfall on the upper slopes of the Alps or the Tian Shan Mountains, the glaciers would extend lower than now without any change in temperature. Although the incompetence of low temperature to cause glaciation and the relative unimportance of the mountains in northeastern Canada and northwestern Europe throw most glacial hypotheses out of court, they are in harmony with the cyclonic hypothesis. The answer of that hypothesis to the problem of the localization of ice sheets seems to be found in certain maps of storminess and rainfall in relation to solar activity. In Figure 2, a marked belt of increased storminess at times of many sunspots is seen in southern Canada. A comparison of this with a series of maps given in Earth and Sun shows that the stormy belt tends to migrate toward in harmony with an increase in the activity of the Sun's atmosphere. If the Sun was sufficiently active, the belt of maximum storminess would apparently pass through Keewatin and Labradorian centers of glaciation instead of well to the south of them, as at present. It would presumably cross another center in Greenland, and then would traverse the fourth of the great centers of Pleistocene glaciation in Scandinavia. It would not succeed in traversing southern Asia, however, any more than it does now, because of the great high-pressure area which develops there in winter. When the ice sheets expand from the main centers of glaciation, the belt of storms will be pushed southward and outward. Thus it might give rise to minor centers of glaciation, such as the patrician between Hudson Bay and Lake Superior, or the centers in Ireland, Cornwall, Wales, and the northern Ural Mountains. As the main ice sheets advanced, however, the minor centers would be overridden and the entire mass of ice would be merged into one vast expanse in the Atlantic portion of each of the two continents. In this connection, it may be well to consider briefly the most recent hypothesis as to the growth and hence the localization of glaciation. In 1911 and more fully in 1915, Hobbes advanced the anticyclonic hypothesis of the origin of ice sheets. This hypothesis has the great merit of focusing attention upon the fact that ice sheets are pronounced anticyclonic regions of high pressure. This is proved by the strong outblowing winds which prevail along their margins. Such winds must, of course, be balanced by inward-moving winds at high levels. Abundant observations prove that such is the case. For example, balloons sent up by Barkhow near the margin of the Antarctic ice sheet revealed the occurrence of inblowing winds, although they rarely occur below a height of 9,000 meters. The abundant data gathered by Gervain on the coast of Greenland indicate that outblowing winds prevail up to a height of about 4,000 meters. At that height, inblowing winds commence and increase in frequency until at an altitude of over 5,000 meters they become more common than outblowing winds. It should be noted, however, that in both Antarctica and Greenland, although the winds are an elevation less than 1,000 meters generally blow outward, there are frequent and decided departures from this rule, so that variable winds are quite commonly mentioned in the reports of expeditions and balloon soundings. The undoubted anticyclonic conditions which Hobbes thus calls to the attention of scientists seems to him to necessitate a peculiar mechanism in order to produce the snow which feeds the glaciers. He assumes that the winds which blow toward the centers of the ice sheets at high levels carry the necessary moisture by which the glaciers grow. When the air descends in the centers of the highs, it is supposed to be chilled on reaching the surface of the ice, and hence to give up its moisture in the form of minute crystals. This conclusion is doubtful for several reasons. In the first place, Hobbes does not seem to appreciate the importance of the variable winds, which he quotes Arctic and Antarctic explorers as describing quite frequently on the edges of the ice sheets. They are one of the many signs that cyclonic storms are fairly frequent on the borders of the ice, though not in its interior. Thus there is a distinct and sufficient form of precipitation annually at work near the margin of the ice, or exactly where the thickness of the ice sheet would lead us to expect. Another consideration which throws grave doubt on the anticyclonic hypothesis of ice sheets is the small amount of moisture possible in the highs because of their low temperature. Suppose, for the sake of argument, that the temperature of the middle of an ice sheet averages 20 degrees Fahrenheit. This is probably much higher than the actual fact, and therefore unduly favorable to the anticyclonic hypothesis. Suppose also that the decrease in temperature from the Earth's surface upward proceeds at a rate of 1 degree Fahrenheit for each 300 feet, which is 50% less than the actual rate for air with only a slight amount of moisture, such as is found in cold regions. Then at a height of 10,000 feet, where the inblowing winds begin to be felt, the temperature would be minus 20 degrees Fahrenheit. At that temperature, the air is able to hold approximately 0.166 grain of moisture per cubic foot when fully saturated. This is an exceedingly small amount of moisture, and even if it were all precipitated, could scarcely build a glacier. However, it apparently would not be precipitated because when such air descends in the center of the anticyclone, it is warmed adiabatically, that is, by compression. On reaching the surface, it would have a temperature of 20 degrees and would be able to hold 0.898 grain of water vapor per cubic foot. In other words, it would have a relative humidity of about 18%. Under no reasonable assumption does the upper air at the center of an ice sheet appear to reach the surface with a relative humidity of more than 20 or 25%. Such air cannot give up moisture. On the contrary, it absorbs it and tends to diminish rather than increase the thickness of the sheet of ice and snow. But after the surplus heat gained by descent has been lost by radiation, conduction, and evaporation, the air may become supersaturated, with the moisture picked up while warm. Hobbes reports that explorers in Antarctica and Greenland have frequently observed condensation on their clothing. If such moisture is not derived directly from the men's own bodies, it is apparently picked up by the ice sheet by the descending air, and not added to the ice sheet by air from aloft. The relation of all this to the localization of ice sheets is this. If Hobbes' anticyclonic hypothesis of glacial growth is correct, it would appear that ice sheets should grow up where the temperature is lowest and the high-pressure areas most persistent, for instance in northern Siberia. It would also appear that so far as the topography permitted, the ice sheets ought to move out uniformly in all directions. Hence the ice sheet ought to be as prominent to the north of the Keewatin and Labradorian centers as to the south, which is by no means the case. Again, in mountainous regions, such as the glacial areas of Alaska and Chile, the glaciation ought not to be confined to the windward slope of the mountains so closely as is actually the fact. In each of these cases, the glaciated region was large enough so that there was probably a true anticyclonic area comparable with that now prevailing over southern Greenland. In both places, the correlation between glaciation and mountain ranges seems much too close to support the anticyclonic hypothesis. For the inblowing winds which, on that hypothesis, bring the moisture are shown by observation to occur at heights far greater than that of all but the loftiest ranges. 2. The sudden coming of glaciation is another problem which has been a stumbling block in the way of every glacial hypothesis. In his Climates of Geologic Times, Schuchert states that the fossils give almost no warning of an approaching catastrophe. If glaciation was solely due to uplift or other terrestrial changes aside from volcanism, Schuchert holds that it would have come slowly and the stages preceding glaciation would have affected life sufficiently to be recorded in the rocks. He considers that the suddenness of the coming of glaciation is one of the strongest arguments against the carbon dioxide hypothesis of glaciation. According to the cyclonic hypothesis, however, the suddenness of the oncoming of glaciation is merely what would be expected on the basis of what happens today. Changes in the sun occur suddenly. The sunspot cycle is only 11 or 12 years long, and even this short period of activity is inaugurated more suddenly than it declines. Again, the climatic record derived from the growth of trees, as given in figures 4 and 5, also shows that marked changes in climate are initiated more rapidly than they disappear. In this connection, however, it must be remembered that solar activity may arise in various ways, as will appear more fully later. Under certain conditions, storminess may increase and decrease slowly. 3. The height of the snow line and of glaciation furnishes another means of testing glacial hypothesis. It is well established that at times of glaciation the snow line was depressed everywhere, but least near the equator. For example, according to Penck, permanent snow extended 4,000 feet lower than now in the Alps, whereas it stood only 1,500 feet below the present level near the equator in Venezuela. This unequal depression is not readily accounted for by any hypothesis depending solely upon the lowering of temperature. By the carbon dioxide and the volcanic dust hypothesis, the temperature presumably was lowered almost equally in all latitudes, but a little more at the equator than elsewhere. If glaciation were due to a temporary lessening of the radiation received from the sun, such as demanded by the thermal solar hypothesis and by the longer periods of Kroll's hypothesis, the lowering would be distinctly greatest at the equator. Thus, according to all these hypotheses, the snow line should have been depressed most at the equator instead of least. The cyclonic hypothesis explains the lesser depression of the snow line at the equator as due to a diminution of precipitation. The effectiveness of precipitation in this respect is illustrated by the present great difference in the height of the snow line on the humid and dry sides of mountains. On the wet eastern side of the Andes near the equator, the snow line lies at 16,000 feet, on the dry western side at 18,500 feet. Again, although the humid side of the Himalayas lies toward the south, the snow line has a level of 15,000 feet, while farther north on the dry side it is 16,700 feet. The fact that the snow line is lower near the margin of the Alps than toward the center points in the same direction. The bearing of all this on the glacial period may be judged by looking again at Figure 3 in Chapter 5. This shows that at times of sunspot activity and hence of augmented storminess, the precipitation diminishes near the heat equator, that is, where the average temperature for the whole year is highest. At present, the great size of the northern continents and their consequent high temperature in summer causes the heat equator to lie north of the real equator, except where Australia draws it to the southward. When large parts of the northern continents were covered with ice, however, the heat equator and the true equator were probably much closer than now, for the continents could not become so hot. If so, the diminution in equatorial precipitation, which accompanies increased storminess throughout the world as a whole, would take place more nearly along the true equator than appears in Figure 3. Hence, so far as precipitation alone is concerned, we should actually expect that the snow line near the equator would rise a little during glacial periods. Another fact, however, must be considered. Köppen's data, it will be remembered, shows that at times of solar activity the Earth's temperature falls more at the equator than in higher latitudes. If this effect were magnified, it would lower the snow line. The actual position of the snow line at the equator during glacial periods thus appears to be the combined effect of diminished precipitation, which would raise the line, and of lower temperature, which would bring it down. Before leaving this subject, it may be well to recall that the relative lessening of precipitation in equatorial latitudes during the glacial epochs was probably caused by the diversion of moisture from the trade wind belt. This diversion was presumably due to the great number of tropical cyclones and to the fact that the cyclonic storms of middle latitudes also drew much moisture from the trade wind belt in summer, where the northern position of the sun drew the belt near the storm track, which was forced to remain south of the ice sheet. Such diversion of moisture out of the trade wind belt must diminish the amount of water vapor that is carried by the trades to equatorial regions. Hence would lessen precipitation in the belt of so-called equatorial calms, which lies along the heat equator rather than along the geographical equator. Another phase of the vertical distribution of glaciation has been the subject of considerable discussion. In the Alps and in many other mountains, the glaciation of the Pleistocene period appears to have had its upper limit no higher than today. This has been variously interpreted. It seems, however, to be adequately explained as due to a decreased precipitation at higher altitudes during the cold periods. This is in spite of the fact that precipitation in general increased with increased storminess. The low temperature of glacial times presumably induced condensation at lower altitudes than now, and most of the precipitation occurred upon the lower slopes of the mountains, contributing to the lower glaciers, while little of it fell upon the highest glaciers. Above a moderate altitude in all lofty mountains, the decrease in the amount of precipitation is rapid. In most cases, the decrease begins at a height of less than 3,000 feet above the base of the main slope, provided the slope is steep. The colder the air, the lower the altitude at which this occurs. For example, it is much lower in winter than in summer. Indeed, the higher altitudes in the Alps are sunny in winter, even when there are abundant clouds lower down. 4. The presence of extensive lakes and other evidences of pluvial climate during glacial periods in non-glaciated regions, which are normally dry, is another of the facts which most glacial hypotheses fail to explain satisfactorily. Beyond the ice sheets, many regions appear to have enjoyed an unusually heavy precipitation during the glacial epochs. The evidence of this is abundant, including numerous abandoned strand lines of salt lakes and an abundance of coarse material in deltas and floodplains. J. D. Whitney, in an interesting but neglected volume, was one of the first to marshal the evidence of this sort. More recently, Free has amplified this. According to him, in the Great Basin region of the United States, 62 basins either contain unmistakable evidence of lakes, or belong to one of the three great lake groups named below. Two of these, the Lake La Hontan and the Lake Bonneville groups, comprise 29 present basins, while the third, the Owen-Sears clan, contains at least 5 large lakes, the lowest being in Death Valley. In Western and Central Asia, a far greater series of salt lakes is found, and most of these are surrounded by strands at high levels. Many of these are described in explorations in Turkestan, the Pulse of Asia, and Palestine and its transformation. There has been a good deal of debate as to whether these lakes actually date from the glacial period, as is claimed by C. E. P. Brooks, for example, or from some other period. The evidence, however, seems to be convincing that the lakes expanded when the ice also expanded. According to the older glacial hypotheses, the lower temperature which is postulated as the cause of glaciation would almost certainly mean less evaporation over the course, and hence less precipitation during glacial periods. To counteract this, the only way in which the level of the lakes could be raised would be because the lower temperature would cause less evaporation from their surfaces. It seems quite impossible, however, that the lowering of temperature, which is commonly taken to have been not more than 10 degrees Celsius, could counteract the lessened precipitation and also cause an enormous expansion of most of the lakes. For example, ancient Lake Bonneville was more than 10 times as large as its modern remnant, Great Salt Lake, and its average depth more than 40 times as great. Many small lakes in the Old World expanded still more. For example, in eastern Persia, many basins which now contain no lake whatever are flooded with vast deposits of lacustrine salt and are surrounded by old lake bluffs and beaches. In northern Africa, similar conditions prevail. Other but less obvious evidence of more abundant rainfall in regions that are now dry is found in thick strata of gravel, sand, and fine salt in the alluvial deposits of floodplains and deltas. The cyclonic hypothesis supposes that increased storminess accounts for pluvial climates in regions that are now dry, just as it accounts for glaciation in the regions of the ice sheets. Figures 2 and 3, it will be remembered, illustrate what happens when the sun is active. Solar activity is accompanied by an increase in storminess in the southwestern United States in exactly the region where elevated strands of diminished salt lakes are most numerous. In Figure 3, the same condition is seen in the region of salt lakes in the Old World. Judging by these maps, which illustrate what has happened since careful meteorological records were kept, an increase in solar activity is accompanied by increased rainfall in large parts of what are now semi-arid and desert regions. Such precipitation would at once cause the level of the lakes to rise. Later, when ice sheets had developed in Europe and America, the high-pressure areas thus caused might force the main storm belt so far south that it would lie over these same arid regions. The increase in tropical hurricanes at times of abundant sunspots may also have a bearing on the climate of regions that are now arid. During the glacial period, some of the hurricanes probably swept far over the lands. The numerous tropical cyclones of Australia, for example, are the chief source of precipitation for that continent. Some of the stronger cyclones locally yield more rain in a day or two than other sources yield in a year. 5. The occurrence of widespread glaciation near the tropics near the Permian, as shown in Figure 7, has given rise to much discussion. The recent discovery of glaciation in latitudes as low as 30 degrees in the Proterozoic is correspondingly significant. In all cases, the occurrence of glaciation in low and middle latitudes is probably due to the same general causes. Doubtless the position and altitude of the mountains had something to do with the matter. Yet taken by itself, this seems insufficient. Today, the loftiest range in the world, the Himalayas, is almost unglaciated, although its southern slope may seem at first thought to be almost ideally located in this respect. Some parts rise over 20,000 feet, and certain lower slopes receive 400 inches of rain per year. The small size of the Himalayan glaciers, in spite of these favorable conditions, is apparently due largely to the seasonal character of the monsoon winds. The strong outblowing monsoons of winter cause about half the year to be very dry, with clear skies and dry winds from the interior of Asia. In all low latitudes, the sun rides high in the heavens at midday, even in winter, and thus melts snow fairly effectively in clear weather. This is highly unfavourable to glaciation. The inblowing southern monsoons bring all their moisture in midsummer at just the time when it is least effective in producing snow. Conditions similar to those now prevailing in the Himalayas must accompany any great uplift of the lands which produces high mountains and large continents in subtropical and middle latitudes. Hence, uplift alone cannot account for extensive glaciation in subtropical latitudes during the Permian and Proterozoic. Figure 7 is displayed on the page, Permian Geography and Glaciation, after Schuchert. The assumption of a great general lowering of temperature is also not adequate to explain glaciation in subtropical latitudes. In the first place, this would require a lowering of many degrees, far more than in the Pleistocene glacial period. The marine fossils of the Permian, however, do not indicate any such condition. In this second place, if the lands were widespread as they appear to have been in the Permian, a general lowering of temperature would diminish rather than increase the present slight efficiency of the monsoons in producing glaciation. Monsoons depend upon the difference between the temperatures of land and water. If the general temperature were lowered, the reduction would be much less pronounced on the oceans than on the lands, for water tends to preserve a uniform temperature, not only because of its mobility, but because of the large amount of heat given out when freezing takes place, or consumed in evaporation. Hence, the general lowering of temperature would make the contrast between continents and oceans less at present in summer, for the land temperature would be brought toward that of the ocean. This would diminish the strength of the inblowing summer monsoons, and thus cut off part of the supply of moisture. Evidence that this actually happened in the cold 14th century has already been given in Chapter 6. On the other hand, in winter the lands would be much colder than now, and the oceans only a little colder, so that the dry outblowing monsoons of the cold season would increase in strength, and would also last longer than at present. In addition to all this, the mere fact of low temperature would mean a general reduction in the amount of water vapor in the air. Thus, from almost every point of view, a mere lowering of temperature seems to be ruled out as a cause of Permian glaciation. Moreover, if the Permian or Proterozoic glacial periods were so cold that the lands above 30 degrees were snow-covered most of the time, the normal surface winds in subtropical latitudes would be largely equatorward, just as the winter monsoons now are. Hence little or no moisture would be available to feed the snowfields which give rise to the glaciers. It has been assumed by Marston Manson and others that increased general cloudiness would account for the subtropical glaciation of the Permian and Proterozoic. Granting for the moment that there could be universal persistent cloudiness, this would not prevent or counteract the outblowing anticyclonic winds so characteristic of great snowfields. Therefore, under the hypothesis of general cloudiness, there would be no supply of moisture to cause glaciation in low latitudes. Indeed, persistent cloudiness in all higher latitudes would apparently deprive the Himalayas of most of their present moisture. For the interior of Asia would not become hot in summer, and no inblowing monsoons would develop. In fact, winds of all kinds would seemingly be scarce, for they arise almost wholly from contrasts of temperature and hence of atmospheric pressure. The only way to get winds and hence precipitation would be to invoke some other agency, such as cyclonic storms, but that would be a departure from the supposition that glaciation arose from cloudiness. Let us now inquire how the cyclonic hypothesis accounts for glaciation in low latitudes. We will first consider the terrestrial conditions in the early Permian, the last period of glaciation in such latitudes. Geologists are almost universally agreed that the lands were exceptionally extensive and also high, especially in the low latitudes. One evidence of this is the presence of abundant conglomerates composed of great boulders. It is also probable that the carbon dioxide in the air during the early Permian had been reduced to a minimum by the extraordinary amount of coal formed during the preceding period. This would tend to produce low temperature and thus made the conditions favorable for glaciation as soon as an accentuation of solar activity caused unusual storminess. If the storminess became extreme when terrestrial conditions were thus universally favorable to glaciation, it would presumably produce glaciation in low latitudes. Numerous and intense tropical cyclones would carry a vast amount of moisture out of the tropics, just as now happens when the sun is active, but on a far larger scale. The moisture would be precipitated on the equatorward slopes of the subtropical mountain ranges. At high elevations, this precipitation would be in the form of snow even in summer. Tropical cyclones, however, as is shown in Earth and Sun, occur in the autumn and winter, as well as in the summer. For example, in the Bay of Bengal, the number recorded in October is 50, the largest for any month, while in November it is 34, and December 14 is compared with the average of 42 for the months of July to September. From January to March, when sunspot numbers averaged more than 40, the number of tropical hurricanes was 143% greater than when the sunspot numbers averaged below 40. During the months from April to June, which also would be times of considerable snowy precipitation, tropical hurricanes averaged 58% more numerous, with sunspot numbers above 40 than with numbers below 40, while from July to September the difference amounted to 23%. Even at this season, some snow falls on the higher slopes, while the increased cloudiness due to numerous storms also tends to preserve the snow. Thus, a great increase in the frequency of sunspots is accompanied by increased intensity of tropical hurricanes, especially in the cooler autumn and spring months, and results not only in a greater accumulation of snow, but in a decrease in the melting of the snow before of more abundant clouds. At such times as the Permian, the general low temperature due to rapid convection and to the scarcity of carbon dioxide, presumably joined with the extension of the lands in producing great high-pressure areas over the lands in middle latitudes during the winters, and thus caused the more northern or mid-latitude types of cyclonic storms to be shifted to the equatorward side of the continents at that season. This would cause an increase of precipitation in winter, as well as during the months when tropical hurricanes abound. Many other circumstances would cooperate to produce a similar result. For example, the general low temperature would cause the sea to be covered with ice in lower latitudes than now, and would help to create high-pressure areas in middle latitudes, thus driving the storms far south. If the sea water were fresher than now, as it probably was to a notable extent, in the Proterozoic, and perhaps to some slight extent in the Permian. The higher freezing point would also further the extension of the ice and help to keep the storms away from high latitudes. If to this there is added a distribution of land and sea such that the volume of the warm ocean currents flowing from low to high latitudes was diminished, as appears to have been the case, there seems to be no difficulty in explaining the subtropical location of the main glaciation in both the Permian and the Proterozoic. An increase of storminess seems to be the key to the whole situation. One other possibility may be mentioned, although little stress should be laid on it. In Earth and Sun, it has been shown that the main storm track in both the northern and southern hemispheres is not concentric with their geographical poles. Both tracks are roughly concentric with the corresponding magnetic poles, a fact which may be important in connection with the hypothesis of an electrical effect of the Sun upon terrestrial storminess. The magnetic poles are known to wander considerably. Such wandering gives rise to variations in the direction of the magnetic needle from year to year. In 1815, the compass in England pointed 24.5 degrees west of north, and in 1906, 70 degrees 45 minutes west. Such a variation seems to mean a change of many miles in the location of the north magnetic pole. Certain changes in the daily march of electromagnetic phenomena over the oceans have led Bauer and his associates to suggest that the magnetic poles may even be subject to a slight daily movement in response to the changes in the relative positions of the Earth and Sun. Thus, there seems to be a possibility that a pronounced change in the location of the magnetic pole in Permian times, for example, may have had some connection with the shifting in the location of the belt of storms. It must be clearly understood that there is as yet no evidence of any such change, and the matter is introduced merely to call attention to a possible line of investigation. Any hypothesis of Permian and Proterozoic glaciation must explain not only the glaciation of low latitudes, but the lack of glaciation and the accumulation of red desert beds in high latitudes. The facts already presented seem to explain this. Glaciation could not occur extensively in high latitudes, partially because, during most of the year, the air was too cold to hold much moisture, but since more because the winds, for the most part, must have blown outward from the cold northern areas, and the cyclonic storm belt was pushed out of high latitudes. Because of these conditions, precipitation was apparently limited to a relatively small number of storms during the summer. Hence, great desert areas must have prevailed at high latitudes. Great aridity now prevails north of the Himalayas and related ranges, and red beds are accumulating in the centers of the great deserts, such as those of the Tarim Basin and the Trans-Caspian. The redness is not due to the original character of the rock, but to intense oxidation, as appears from the fact that along the edges of the desert, and wherever occasional floods carry sediment far out into the midst of the sand, the material has the ordinary brownish shades. As soon as one goes out into the places where the sand has been exposed to the air for a long time, however, it becomes pink and then red. Such conditions may have given rise to the high degree of oxidation in the famous Permian red beds. If the air of the early Permian contained an unusual percentage of oxygen because of the release of that gas by the great plant beds which formed coal in the preceding era, as Chamberlain had thought probable, the tendency to produce red beds would still be further increased. It must not be supposed, however, that these conditions would absolutely limit glaciation to subtropical latitudes. The presence of early Permian glaciation in North America at Boston and in Alaska and the Falkland Islands of the South Atlantic Ocean proves that at least locally there was sufficient moisture to form glaciers near the coast in relatively high latitudes. The possibility of this would depend entirely upon the form of the lands and the consequent course of ocean currents. Even in those high latitudes, cyclonic storms would occur unless they were kept out by conditions of pressure such as have been described above. The marine faunas of Permian age in high latitudes have been interpreted as indicating mild oceanic temperatures. This is a point which requires further investigation. All motions during times of slight solar activity are a necessary consequence of the cyclonic hypothesis, as will appear later. The present cold oceans seem to be the expectable result of the Pleistocene glaciation and of the present relatively disturbed condition of the Sun. If a sudden disturbance threw the solar atmosphere into violent commotion within a few thousand years during Permian times, glaciation might occur as described above, where the oceans were still warm. In fact, their warmth would increase evaporation, while the violent cyclonic storms and high winds would cause heavy rain and keep the air cool by constantly raising it to high levels, where it would rapidly radiate its heat into space. Nevertheless, it is not yet possible to determine how warm the oceans were at the actual time of the Permian glaciation. Some forms formerly reported as Permian are now known to be considerably older. Moreover, others of undoubted Permian age are probably not strictly contemporaneous with the glaciation. So far back in the geological record, it is very doubtful whether we can date fossils within the limits of, say, 100,000 years. Yet a difference of 100,000 years would be more than enough to allow the fossils to have lived either before or after the glaciation, or in an interglacial epoch. One such epoch is known to have occurred, and 9 others are suggested by the interstratification of glacial, till, and marine sediments in eastern Australia. The warm currents which would flow poleward in interglacial epochs must have favoured a prompt reintroduction of marine faunas driven out during times of glaciation. Taken all in all, the Permian glaciation seems to be accounted for by the cyclonic hypothesis quite as well as does the Pleistocene. In both these cases, as well as in the various pulsations of historic times, it seems to be necessarily merely to magnify what is happening today in order to reproduce the conditions which prevailed in the past. If the conditions which now prevail at times of sunspot minima were magnified, they would give the mild conditions of interglacial epochs and similar periods. If the conditions which now prevail at times of sunspot maxima are magnified a little, they seem to produce periods of climatic stress such as those of the 14th century. If they are magnified still more, the result is apparently glacial epochs like those of the Pleistocene, and if they are magnified to a still greater extent, the result is Permian or Proterozoic glaciation. Other factors must indeed be favourable, for climatic changes are highly complex and are unquestionably due to a combination of circumstances. The point which is chiefly emphasized in this book is that among those several circumstances, changes in cyclonic storms due apparently to activity of the sun's atmosphere must always be reckoned. End of Section 8. Section 9 of Climatic Changes, Their Nature and Causes by Ellsworth Huntington. This LibriVox recording is in the public domain, recorded by Leon Harvey. Chapter 9. The Origin of Loess. One of the most remarkable formations associated with glacial deposits consisted of vast sheets of fine-grained, yellowish, wind-blown material called loess. Somewhat peculiar climatic conditions evidently prevailed when it was formed. At present, similar deposits are being laid down only near the leeward margin of great deserts. The famous loess deposits of Jonah in the lee of the desert of Gobi are examples. During the Pleistocene period, however, loess accumulated in a broad zone along the margin of the ice sheet at its maximum extent. In the Old World, it extended from France across Germany and through the Black Earth region of Russia into Siberia. In the New World, a still larger area is loess covered. In the Mississippi Valley, tens of thousands of square miles are mantled by a layer exceeding 20 feet in thickness and in many places approaching 100 feet. Neither the North American nor the European deposits are associated with the desert. Indeed, loess is lacking in the western and drier parts of the Great Plains and is best developed in the well-watered states of Iowa, Illinois, and Missouri. Part of the loess overlies the non-glacial materials of the Great Central Plain, but the northern portions overlie the drift deposits of the first 3 glaciations. A few traces of loess are associated with the Kansan and Illinoisan, the second and third glaciations, but most of the American loess appears to have been formed at approximately the time of the Iowan or fourth glaciation, while only a little overlies the drift sheets of the Wisconsin age. The loess is thickest near the margin of the Iowan till sheet and thins progressively both north and south. The thinning southward is abrupt along the stream divides, but very gradual along the larger valleys. Indeed, loess is abundant along the bluffs of the Mississippi, especially the East Bluff, almost to the Gulf of Mexico. It is now generally agreed that all typical loess is wind-blown. There is still much question, however, as to its time of origin, and thus indirectly as to its climatic implications. Several American and European students have thought that the Loess dates from the interglacial times. On the other hand, Penck has concluded that the Loess was formed shortly before the commencement of the glacial epochs, while many American geologists hold that the Loess accumulated while the ice sheets were at approximately their maximum size. W. J. McGee, Chamberlain and Salisbury, Keyes, and others lean toward this view. In this chapter, the hypothesis is advanced that it was formed at the one other possible time, namely immediately following the retreat of the ice. These four hypotheses as to the time of origin of Loess imply the following differences in its climatic relations. If Loess was formed during typical interglacial epochs, or toward the close of such epochs, profound general aridity must seemingly have prevailed in order to kill off the vegetation and thus enabled the wind to pick up sufficient dust. If the Loess was formed during times of extreme glaciation when the glaciers were supplying large quantities of fine material to outflowing streams, less aridity would be required, but there must have been sharp contrast between wet seasons in summer when the snow was melting and dry seasons in winter when the storms were forced far south by the glacial high pressure. Alternate floods and droughts would thus affect broad areas along the streams. Hence arises the hypothesis that the wind obtained the Loess from the floodplains of streams at times of maximum glaciation. If the Loess was formed during the rapid retreat of the ice, alternate summer floods and winter droughts would still prevail, but much material could also be obtained by the winds, not only from the floodplains but also from the deposits exposed by the melting of the ice and not yet covered by vegetation. The evidence for and against the several hypotheses may be stated briefly. In support of the hypothesis of the interglacial origin of Loess, Schimmeck and others state that the glacial drift which lies beneath the Loess commonly gives evidence that some time elapsed between the disappearance of the ice and the deposition of the Loess. For example, abundant shells of land snails in the Loess are not of the sort now found in colder regions, but resemble those found in the drier regions. It is probable that if they represented a glacial epoch, they would be depopulated by the cold, as are the snails of the far northern regions. The gravel pavement discussed below seems to be strong evidence of erosion between the retreat of the ice and the deposition of the Loess. During the second hypothesis, namely that the Loess accumulated near the close of the interglacial epoch rather than the midst of it, we may follow Penck. The mammalian fossils seem to him to prove that the Loess was formed while boreal animals occupied the region, for they include remains of the hairy mammoth, woolly rhinoceros, and reindeer. On the other hand, the typical interglacial beds not far away yield remains of species characteristic of milder climates, such as the elephant, the smaller rhinoceros, and the deer. In connection with these facts, it should be noted that occasional remains of tundra vegetation and of trees are found beneath the Loess, while in the Loess itself certain steppe animals, such as the common gopher or spermophile, are found. Penck interprets this as indicating a progressive desiccation culminating just before the oncoming of the next ice sheet. The evidence advanced in favor of the hypothesis that the Loess was formed when glaciation was near its maximum includes the fact that if the Loess does not represent the outwash from the Ioan ice, there is little else that does, and presumably there must have been outwash. Also, the distribution of Loess along the margins of streams suggests that much of the material came from the floodplains of overloaded streams flowing from the melting ice. Although there are some points in favor of the hypothesis that the Loess originated 1. In strictly interglacial times, 2. At the end of interglacial epochs, and 3. At times of full glaciation, each hypothesis is much weakened by evidence that supports the others. The evidence of boreal animals seems to disprove the hypothesis that the Loess was formed in the middle of a mild interglacial epoch. On the other hand, Penck's hypothesis as to Loess at the end of interglacial times fails to account for certain characteristics of the lowest part of the Loess deposits and of the underlying topography. Instead of normal valleys and consequent prompt drainage, such as ought to have developed before the end of a long interglacial epoch, the surface on which the Loess lies shows many undrained depressions. Some of these can be seen in exposed banks, while many more are inferred from the presence of shells of pond snails here and there in the overlying Loess. The pond snails presumably lived in shallow pools occupying depressions in the uneven surface left by the ice. Another reason for questioning whether the loess was formed at the end of an interglacial epoch is that this hypothesis does not provide a reasonable origin for the material which composes the loess. Near the Alps, where the loess deposits are small and where glaciers probably persisted in the interglacial epochs and thus supplied floodplain material in large quantities, this does not appear important. In the broad upper Mississippi Basin, however, and also in the Black Earth region of Russia, there seems to be no way to get at the large body of material composing the loess except by assuming the existence of great deserts to windward. But there seems to be little or no evidence of such deserts where they could be effective. The mineralogical character of the loess of Iowan age proves that the material came from granite rocks, such as formed a large part of the drift. The nearest extensive outcrops of granite are in the southwestern part of the United States, nearly 1,000 miles from Iowa and Illinois. But the loess is thickest near the ice margin and thins toward the southwest and in other directions, whereas if its source were the southwestern desert, its maximum thickness would probably be near the margin of the desert. The evidence cited above seems inconsistent not only with the hypothesis that the loess was formed at the end of an interglacial epoch, but also with the idea that it originated at times of maximum glaciation, either from riverborne sediments or from any other source. A further and more convincing reason for this last conclusion is a probability that almost the certainty that when the ice advanced, its front lay close to areas where the vegetation was not much thinner than that which today prevails under similar climatic conditions. If the average temperature of glacial maxima was only 6 degrees Celsius lower than that of today, the conditions just beyond the ice front, when it was in the lowest region from the southern Illinois to Minnesota, would have been like those now prevailing in Canada, from New Brunswick to Winnipeg. The vegetation there is quite different from the grassy, semi-arid vegetation of which evidence is found in the loess. The roots and stalks of such grassy vegetation are generally agreed to have helped produce the columnar structure which enables the loess to stand with almost vertical surfaces. We are now ready to consider the probability the loess accumulated mainly during the retreat of the ice. Such a retreat exposes a zone of drift to the outflowing glacial winds. Most glacial hypotheses, such as that of uplift or depleted carbon dioxide, call for a gradual retreat of the ice scarcely faster than the vegetation could advance into the abandoned area. Under the solar cyclonic hypothesis, on the other hand, the climatic changes may have been sudden and hence the retreat of the ice may have been much more rapid than the advance of vegetation. Now, wind-blown materials are derived from places where vegetation is scanty. Scanty vegetation on good soil, it is true, is usually due to aridity, but may also result because the time since the soil was exposed to the air has not been long enough for the soil to be sufficiently weathered to support vegetation. Even when weathering has had full opportunity, as when sandbars, mudflats, and floodplains are exposed, vegetation takes root only slowly. Moreover, storms and violent winds may prevent the spread of vegetation, as is seen on sandy beaches, even in distinctly humid regions like New Jersey and Denmark. Thus it appears that unless the retreat of the ice were as slow as the advance of vegetation, a barren area of more or less width must have bordered the retreating ice and formed an ideal source of loess. Several other lines of evidence seemingly support the conclusion that the loess was formed during the retreat of the ice. For example, Schimmick, who has made almost a lifelong study of the Iowan loess, emphasized the fact that there is often an accumulation of stones and pebbles at its base. This suggests that the underlying till was eroded before the loess was deposited upon it. The first reaction of most students is to assume that, of course, this is due to running water. That is possible in many cases, but by no means in all. So widespread a sheet of gravel could not be deposited by streams without destroying the irregular basins and hollows of which we have seen evidence where the loess lies on glacial deposits. On the other hand, the wind is competent to produce a similar gravel pavement without disturbing the old topography. Desert pavements are a notable feature of most deserts. On the edges of an ice sheet, as Hobbes has made us realize, the commonest winds are outward. They often attain a velocity of 80 miles an hour in Antarctica and Greenland. Such winds, however, usually decline rapidly in velocity only a few score miles from the ice. Thus their effect would be to reduce rapid erosion of the freshly barred surface near the retreating ice. Pebbles would be left behind as a pavement, while sand and then loess would be deposited farther from the ice where the winds were weaker and where vegetation was beginning to take root. Such a decrease in wind velocity may explain the occasional vertical gradation from gravel through sand to coarse loess and then to normal fine loess. As the ice sheet retreated, the wind in any given place would gradually become less violent. As the ice continued to retreat, the area where loess was deposited would follow at a distance, and thus each part of the gravel pavement would in turn be covered with loess. The hypothesis that loess is deposited while the ice is retreating is in accord with many other lines of evidence. For example, it accords with the boreal character of the mammal remains as described above. Again, the advance of vegetation into the barren zone along the front of the ice would be delayed by the strong outblowing winds. The common pioneer plants depend largely on the wind for the distribution of their seeds, but the glacial winds would carry them away from the ice rather than toward it. The glacial winds discourage the advance of vegetation in another way, for they are drying winds, as are almost all winds blowing from a colder to a warmer region. The fact that remains of trees sometimes occur at the bottom of the loess probably means that the deposition of loess extended into the forests, which almost certainly persisted not far from the ice. This seems more likely than that a period of severe aridity before the advance of the ice killed the trees and made a steppe or desert. Peng's chief argument in favor of the formation of loess before the advance of the ice rather than after is that since loess is lacking upon the youngest drift sheet in Europe, it must have been formed before rather than after the last or worm advance of the ice. This breaks down on two counts. First, on the corresponding Wisconsin drift sheet in America, loess is persistent, in small quantities to be sure, but unmistakably present. Second, there is no reason to assume that conditions were identical at each advance and retreat of the ice. Indeed, the fact that in Europe, as in the United States, nearly all the loess was formed at one time, and only a little is associated with the other ice advances, points clearly against Peng's fundamental assumption that the accumulation of loess was due to the approach of a cold climate. Having seen that the loess was probably formed during the retreat of the ice, we are now ready to inquire what conditions the cyclonic hypothesis would postulate in the loess areas during the various stages of a glacial cycle. Figure 2 in Chapter 4 gives the best idea of what would apparently happen in North America, and events in Europe would presumably be similar. During the 9 maximum years on which Figure 2 is based, the sunspot numbers averaged 70, while during the 9 minimum years they averaged less than 5. It seems fair to suppose that the maximum years present, the average conditions which prevailed in the past at times when the sun was in a median stage between the full activity which led to glaciation and the mild activity of the minimum years which appeared to represent interglacial conditions. This would mean that when a glacial period was approaching, but before an ice sheet had accumulated to any great extent, a crescent-shaped strip from Montana through Illinois to Maine would suffer a diminution in storminess ranging up to 60% as compared with the interglacial conditions. This is in strong contrast with an increase in storminess amounting to 75 or even 100% both in the boreal storm belt in Canada and the subtropical belt in the southwest. Such a decrease in storminess in the central United States would apparently be most noticeable in summer, as is shown in Earth and Sun. Hence it would have a maximum effect in producing aridity. This would favor the formation of loess, but it is in discussion of climate, as in most subjects, a peculiar psychological phenomenon is observable. Everyone sees the necessity of explaining conditions different from those that now exist, but few realize that present conditions may be abnormal, and that they need explanation just as much as do others. Because of this tendency, glaciation is being discussed with the greatest fullness, while there has been much neglect not only of the periods when the climate of the earth resembled that at present, but also of the vastly longer periods when it was even milder than now. Doubtful whether the aridity would become extreme enough to explain such vast deposits as are found throughout the large parts of the Mississippi Basin. This would demand that hundreds of thousands of square miles should become almost absolute desert, and it's not probable that any such thing occurred. Nevertheless, according to the cyclonic hypothesis, the period immediately before the advent of the ice would be relatively dry in the central United States, and to that extent favourable to the work of the wind. As the climatic conditions became more severe and the ice sheet expanded, the dryness and lack of storms would apparently diminish. The reason, as has been explained, would be the gradual pushing of the storms southward by the high pressure area which would develop over the ice sheet. Thus, at the height of a glacial epoch, there would apparently be great storminess in the area where the lowest is found, especially in summer. Hence, the cyclonic hypothesis does not accord with the idea of great deposition of Lewis at the time of maximum glaciation. Finally, we come to the time when the ice was retreating. We have already seen that not only the river floodplains, but also vast areas of fresh glacial deposits would be exposed to the winds, and would remain without vegetation for a long time. At that very time, the retreat of the ice sheet would tend to permit the storms to follow paths determined by the degree of solar activity in place of the far southerly plains to which the high atmospheric pressure over the expanded ice sheet had previously forced them. In other words, the conditions shown in Figure 2 would tend to reappear when the sun's activity was diminishing and the ice sheet was retreating, just as they had appeared when the sun was becoming more active and the ice sheet was advancing. This time, however, the semi-arid conditions arising from the scarcity of storms would prevail in a region of glacial deposits and widely spreading river deposits, few or none of which would be covered with vegetation. The conditions would be almost ideal for aeolian erosion and for the transportation of Lewis by the wind to areas a little more remote from the ice, where grassy vegetation had made a start. The cyclonic hypothesis also seems to offer a satisfactory explanation of variations in the amount of Lewis associated with the several glacial epochs. It attributes these to differences in the rate of disappearance of the ice, which in turn varied with the rate of decline of solar activity and storminess. This is supposed to be the reason why the Iowan Lewis deposits are much more extensive than those of the other epochs, for the Iowan ice sheet presumably accomplished part of its retreat much more suddenly than the other ice sheets. The more sudden the retreat, the greater the barren area where the winds could gather fine bits of dust. Temporary readvances may also have been so distributed and of such intensity that they frequently accentuated the conditions shown in Figure 2, thus making the central United States dry soon after the exposure of great amounts of glacial debris. This closeness with which the cyclonic hypothesis accords with the facts as to the Lewis is one of the pleasant surprises of the hypothesis. The first draft of Figure 2 and the first outlines of the hypothesis were framed without thought of the Lewis, yet so far as can now be seen, both agree closely with the conditions of Lewis formation. End of Section 9.